Hello. Let me just set up my chart. Okay, now I'm changing to full screen. Right. So last video I did uh, trigonometric substitution and trigonometric integrals. Let me just do one question from this and then I will move on to the next chapter, which is partial fractions, finally. But this takes so long to load. Which question should I do? Maybe 139. Yeah, x squared and root 1 minus x squared. When you have a case of a square minus x square, you substitute sine theta, right? Yeah, you substitute sine theta. One minus sine square theta. This would be just cos theta. Yeah. Instead of dx, I will write cos theta d theta. Now what about this? Hold on. Sine is 1 over cosecant, right? That will give me cotangent theta minus cotangent theta plus c. Question 139. Whoops. Need to write it in terms of x. So cos theta over sine theta plus c negative. This is just x. And then this is x as well. So x squared 3.3139. Yeah, 1 minus x squared over x plus c. Yes, that's correct. Okay. Can you guys see my mouse? There's like no one here. Anyways, let's go to the next chapter. Partial fractions. In this section, we examine the method of partial fraction decomposition, which allows us to decompose rational functions into sums of simpler, more easily integrated rational functions. Using this method, we can rewrite an expression such as 3x over x squared minus x minus 2 as an expression such as 1 over x minus 1 plus 2 over x minus 2. The key to the method of partial fraction decomposition is being able to anticipate the form that the decomposition of the rational function will take. As we shall see, this form is both predictable and highly dependent on the factorization of the denominator of the rational function. It is also extremely important to keep in mind that partial fraction decomposition can be applied to a rational function p x over qx only if degree of p is less than the degree of q. In this case, in the case when degree of p is more than or equal to degree of q, we must perform long division to rewrite the quotient p over q in the form of a plus r over q, where degree of r is less than the degree of q. We then do the partial fraction decomposition on r over q. Okay, for this case, x squared plus 3x plus 5 x plus 1. I can use long division here. So we multiply by x, we get x squared plus x. We subtract, we are left with 3x minus x plus 5. That leaves us with 2x. and then we times it by 2, 2x plus 2, 5 minus 2 is 3. So this is is this correct? So if I over here, if I multiply the top and bottom by x plus 1, then I would have x squared plus 2x. Yeah, I think it's correct. Then I can separate them. So let me see. So x becomes x square over 2, and then 2 becomes 2x plus it with 3 integral plus c, but I will add the plus c after integrating this. What do we do here? A derivative of ln x plus 1 is 1 over x plus 1 So is that correct? Yes. Non-repeated linear factors. If q of x can be factored as a1x plus b, a2x plus b, and so on, where each linear factor is distinct, then it is possible to find constants a1, a2, an satisfying this. The proof of such constants exist. The proof that such constants exist is beyond the scope of this course. In this next example, we shall see how to use partial fractions to integrate a rational function of this type. Non-repeated linear factors. Supposed to do, but let me just try. Three x plus 2 3 squared minus x squared minus 2x. Now I do x cubed, I get 3x cubed. Sorry, if I do x squared, I mean 3x squared plus 2x squared. Actually, let's do 1 over 3 squared. 2 over 3. This and this cancel. Minus 1 minus 2 over 3. X squared minus 2x. And this is minus 5 over 3. I don't know if this is correct. Hold on, what do they do? So this is x squared plus x minus 2x minus 2. This would give this. So then I guess this cannot be broken down into A, B, and C. This is going to take really long. Hold on. dividing it like this, right? Okay, I understand. Wait, never mind. B x and x minus 2 plus it with C x and x minus plus 1. Guess we don't need the denominator. So how do we find? Let's see. If x is minus 1, this would mean 2 minus 3 minus b. Whoops. It then means minus 1 over 3 is equal to b, because this and this will cancel out. If x is 2, that means this and this will cancel out. So 3 times 2, 6 plus 2, 8. 2, 3. And then x is 0. Which means 2 is equal to a minus 2. So a is equal to negative 1. Four over 3 minus 1 over 3 minus 1. I see. And then minus 1 over x x minus 1, right? No, wait, it's x plus 1, not plus, 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 and then x minus 2. Then I guess the answer is correct. And let's try the next one. And then this becomes x. Over here I have to use partial fractions. then this would mean plus it with b, right? Is half wait a minute. And then this, wait, why is 1 is 11/4, like b is, one of them is 11/4 and the other one should be minus half, right? Not 1/4. If x is -2, a times -4, then 5 minus 3 is 2. Then we are left with a is equal to minus half. I think there's a mistake here. Never mind. Applying partial fractions after a substitution. Should I do this one? It seems tough, so let's just try it. Cos x okay, let's say u is equal to sine x, then du is equal to cos x dx, which means so that means so u is equal to 0 implies 1 is equal to minus a, or a is equal to minus 1, and then u is equal to 1 implies now 1 is equal to b. So then that means so, and u is what? U is sine x. So I just have to replace u with sine x and I'll get the final answer. In sine x For some application, we need to integrate rational expressions that have denominator with repeated linear factors. That is, rational functions with at least one factor of the form ax plus b to the power of n, where n is a positive integer greater than or equal to 2. If the denominator contains the repeated linear factor ax plus b to the power of n, and then the decomposition must contain like this. Oh, I see. So one decomposition will have 2x minus 1 and then another with 2x minus 1 squared. So let's try this. I think this is how it's supposed to work. So let's try. A is now let's say x is equal to 1, then negative 1, this becomes 0, this becomes 0, this becomes 2, minus 1 is 1, this becomes c. So c is equal to negative 1. Now let's say x is equal to half. So half minus 2 I think minus 7.5. No. If I add 1 to this, it will come minus 0.5. Add another one, it will come plus 0.75, plus 0.5. This will come 0. this will become 0, and then b will be half minus 1 is minus half. What about a though? Three minus 1. How do you get 2? Plus 3x minus 3. C is negative 1, so I'll just write minus 2x minus 1 squared 2ax squared minus 2a, no, minus 3ax plus a. And then is it supposed to take this long? Two times 2 is 4x squared Is it supposed to take this long after getting a common? What's the method of equating coefficient? A plus B plus C is equal to 0. How did they get this? So the x square is 2a minus 4. Then 3 plus 4 is 7. Then the x part, 3 plus 4 is 7. 7 minus 3a. And then the normal part is plus a minus 4. I think a is 4 over 2. So then this will be 0. What is the actual answer? At this point, it may seem we have run out of, or since B and C, we can substitute in these values for any choice of x not previously used. A is equal to 2. So if A is 2, this will become 0, which makes sense. 2 minus 4 is minus 2, so this part makes sense. So this will become 1x, so this makes sense. That means A is equal to 2. Going back to our integral, 2 over 2x minus 1 plus it with b, which is 3 over 2x minus 1 square. And then minus 1, so 1 minus x. Actually, how should I do this one? So this is wait, ln of no, not ln. Let's say u is equal to, let's remove all this. Which implies du is equal to 2dx. No, wait, hold on. This is u to the power of minus 2. So then this will become minus 1 over 1. So then this will be ln of x minus half plus 3 over 2 2x minus 1. Oops, no, this is I don't get how 2 over 2x minus 1 integrating this gives ln of 2x minus 1. If we derivate this, if we derivate ln of 2x minus 1, we get 1 over 2x minus 1 times 2, which I guess makes sense. Wait. Um, oh, I see. This ln of half is inside the plus c over here. The general method to decompose the rational function pq over px, use the following step. Make sure degree of pq is less than the degree. Make sure the degree of p is less than the degree of q. If not, perform long division of polynomials. If q can be factored as ax plus a1, x plus b1, a2x plus b2, and so on, where each linear factor is distinct, then it is possible to find the constants a1, a2, so on. If q contains the repeated linear factor ax plus b to the power of n, then the decomposition must contain this. For each irreducible quadratic factor ax squared plus bx plus c that q contains, the decomposition must include this. For each repeated irreducible quadratic factor ax squared plus bx plus c to the power of n, the decomposition must include this. I don't think we did. I don't think we did irreducible quadratic factors. Recall that if the quadratic ax squared plus bx plus c is reducible, recall that the quadratic ax squared plus bx plus c is reducible if ax squared plus bx plus c is equal to 0, has no real zeros. Oh, I see that then you can't separate it. The decomposition must contain x plus b. Okay, they split this up, and this cannot be reduced further, x squared plus 1, so they wrote ax plus b over here, and then they solved it. Partial fractions with an irreducible quadratic factor. How would you split this? You can start by factoring x cubed minus 8. I think the factoring is the hardest part, because I did not imagine this. Maybe if it has a solution, if x cubed minus 8 is equal to 0 has a solution, then there must be a particular x. I'm guessing x squared plus 2x plus 4 doesn't have. Yeah, that makes sense because it will be above the x-axis. Find the volume of the solid of revolution obtained by revolving the region enclosed by the graph of this and the x-axis over the interval 0, 1 about the y-axis. So you use the cylindrical shells method, right? I got these pictures from the book. Do by f of x, x, d of x. So x square plus 1 square I can take 2 pi out. And then I guess I can do this. X squared plus 1 doesn't have it's irreducible, right? think I can write this as like that. I don't know if this is right. Yeah, this is irreducible. Which is right. X square plus 1. Ax cubed plus ax plus bx square plus b plus c. A has to be 1, right? Now let me think. So that means 0 is equal to ax. But a is 1. X square plus 1, it's never going to be 0. or this is repeated irreducible. Wait. Okay, we need this as well. Cx plus d. Cx plus 1. I don't understand. Can this even be solved? Ax cubed plus ax bx squared plus b. A is equal to 1. Then the x cube will match. There's only a one coefficient with x squared, which is b. Hold on. I understand. Since there's only one coefficient with x squared, then b is 0. Also, d is 0 because there's no constant on this side. So we are left with x and cx. X is c plus 1. But c plus 1 is also 0. Therefore, c is negative 1. And then we are left with 2 pi 1 0. A is 1, b is 0. So this is x and this is minus x, right? X over x squared plus 1. Then minus Is this correct? Don't know why I'm... Oh, this is squared. Let me think about how I can derive this. Derivative of x squared plus 1 negative to the power of negative to the power of actually ln of x squared plus 1. I give you. And the derivative of inside is 2x. And then the derivative of x squared plus 1 give you a minus squared plus 1 negative 2 and then 2x. So all this is 2 pi. Ln of x squared plus 1 over 2 subtracted with if I bring minus 2 to the other side, x squared plus 1 ln of 1 is 0, right? Minus it with if I have 1 over here, 1 plus 1 is 2, 2 times 2 is 4, and then minus that with 0 over here, then I'm left with 2. Let me see if this is correct. Pi ln of 2 minus half. pi ln of 2, then multiply 2 over here, minus and minus becomes plus, minus comes plus, and then minus again comes minus 1. So yeah, it is minus half. It's really long. Like, it's not exactly fun. Okay, let's go to the next chapter. I think this one involves other integrals, and most probably it will involve arc sin h, or maybe just sin h. Hyperbolic functions. Think derivative of arc sin h. Yeah, this part, derivative of arc sine is your sine a, and then the root of a square minus x square. It is using sin h, not arc sine. Derivative of arc sine. So 1 plus. So what? So arc sine hy, derivating arc sine hy gives you 1 over 1 plus y square. Use the table formula to evaluate this. Instead of 16, I have to write 4 square, right? Computer algebra systems. Okay, never mind. I'll just do this question and move on to the next chapter. The next, like, after this, they're telling me to use computer systems. Wolfram. So 16 minus 16 minus Oh, I see. U is equal to e to the power of x. Okay, and then we have to evaluate this. I don't want to do the entire thing. Should I do this next stream or this stream? What is this anyways? Trapezoid rule. Oh, I know this. I think I would read about it, but I wouldn't do any of the uh, exercises. Earlier in this text, we define the definite integral of a function over an interval as a limit of Riemann sums. In general, any Riemann sum of a function f of x over an interval a, b may be viewed as an estimate of the area under the graph. Okay, the midpoint rule for estimating a definite integral uses Riemann sum with subinterval of equal width and the midpoint mi of its subinterval in place of xi. This x star is any point in between, right? Because I thought x star was the midpoint. Mi be the midpoint of the ith subinterval. Okay. This is the area of the rectangle. Okay, the trapezoid rule. Okay, I'm going to just guess what the trapezoid rule is. I did the trapezoid rule when I was learning integration in grade 12 or 13. So here is a graph. Let's do this. We want to find the area. We take like many trapezoids. So area of a trapezoid is this plus this. A plus bh over 2. bh a plus bh over 2, and then between a b is approximately equal to x0 plus x1 h, which is the width, over 2 plus it with plus x2 over 2 plus it with all of them. Yeah, you get the point. all the way till xn minus 1 plus xn times delta x over 2, which is then take delta x over 2 out, plus it with this, and this appears twice. Oops, 2 n minus 1, and then the last one appears once. So delta x over 2 times it with this is a and this is b. This is 2 times this is what I'm guessing they will do. Whoops, it's not x, it's f of x. Yeah, well, it's not x, it's f of x. You get the point. If b is our estimate of some quantity having an actual value of a, then the absolute error is given by a minus b modulus. The relative error is the error as a percentage of the absolute value is given by this. Calculate the absolute and relative error in the estimate of using the midpoint rule found in example 3.39. So going to example 3.39, the final answer they used was 0. Yeah, they already calculated the error, 0.0052. What do you mean by relative error? The absolute error is given by this. The relative error is given by this. Or relative error, like what is the percentage of the error in terms of the actual answer? Like what percent of the actual answer is the relative error? What value of n should we use to generate an estimate of this to be accurate to within 0.01? We use the midpoint rule. With the midpoint rule, we estimated areas of regions under the curves by using rectangles. In a sense, we approximated the curve with piecewise constant functions. With the trapezoid rule, we approximated the curve by using piecewise linear functions. What if we were instead to approximate a curve using a piecewise quadratic functions? With Simpson's rules, we do just this. We partition the interval into even number of subintervals, each of equal width. Over the first pair of subintervals, we approximate this with p, where p is equal to ax squared plus bx plus c. It's a quadratic function passing through these points. Now the next pair of subintervals, we approximate this with the integral of another quadratic function passing through these 3 points. This process is continued with each successive pair of subintervals. This is going to take really long. Okay, next. Improper integrals. I think this is the last thing, and then can end the chapter finally. Integrating over an infinite interval. How should we go about defining an integral of the type a to all the way to plus infinity f of x t of x? We can integrate a t or any value of t, so it's reasonable to look at the behavior of this integral as we substitute larger values of t. That makes sense. In each case, if the limit exists, then the improper integral is said to converge. If the limit does not exist, then the improper integral is said to diverge. Okay. In our first example, we return to the question we posed at the start of this section. Is the area between the graph of f of x 1 over x and the x-axis over the interval finite or infinite? I don't think 1 over x converges. Let's just f of x a b 1 over x d of x. This will give ln of x b a. Then this will be ln of b minus ln of a. Now let b go to infinity and a equals 1, so that means minus 0. ln of 1 is 0. So I do ln of x. ln of x keeps increasing, right? So it's undefined. The region is infinite. Find the volume the solid obtained by revolving the region bounded by the graph. I keep forgetting this. For the area, for the volume, we do pi f of x squared, right? Yeah. Pi f of x squared pi from A to B 1 over x squared d of x by guess it's this. I'm not sure about this. Minus x to the power of minus 1, if we derivate that, get x to the power of minus 2. I guess that's correct. And then this becomes a minus 1 over b minus is plus 1 over a. One over a minus 1 over b. Now let a is equal to 1 and b goes to infinity. So pi 1 minus 0 give me pi. That's the volume. In conclusion, although the area of the region between the x-axis and the graph of f of x is equal to 1 over x over the interval 1 to positive infinity is infinite, the volume of the solid generated by revolving this region about the x-axis is finite. This solid is generally known as Gabriel's horn. In the chapter opener, we stated the following problem. Suppose that at a busy intersection, traffic accidents occur at the average rate of 1 every 3 months. After residents complained, changes were made to the traffic lights at the intersection. It has now been 8 months since the changes were made and there have been no accidents. Were the changes effective, or is the 8-month interval without an accident a result of chance? Probability theory tells us if the average time between events is k, the probability of x, the time between events, is between a and b is given by this function I'll just look at the answer. Okay. Evaluating an improper integral on minus infinity to positive infinity. Derivative by 2x. That doesn't make sense. I forgot what's the integral of this. If we say u is equal to x, then du is equal to dx, and is equal to u dv uv minus v du. v du. If we derive this, derivative of the first takes the second, and never mind. Integral a b x e to the power of x e to the power of b minus a e to the power of a if a is 0 and b is going to infinity, then that means the integral diverges. But if b is 0, wait a minute. If I do ab plus bc, it diverges, right? Oops, no, I wrote the wrong thing. Wait, hold on. If a is 0, sorry, if b is 0, this part goes away. Minus 1 would stay, and then this minus infinity, this would go towards 0, right? And then what about this though? How did it get this? E to the power of minus, oh yeah, that makes sense. I don't understand what they just did. Okay, I understood this e to the power of minus t. I think they took the derivative of both sides with respect to t, and this, you ended up with minus 1 over e to the power of minus t. and then minus e to the power of t is equal to 0 by L'Hopital's rule. So that makes sense. And equal to -1. If a tends to positive infinity and b goes to 0, a to positive infinity, wait, hold on. Shouldn't this be +1? Because when this is 0, this becomes -1. Yeah, this becomes -1, but you're subtracting it, so it becomes +1. E to the power of p times p minus e to the power of p. This part comes from this. But as for this, if a is 0, then e to the power of a times -1. But e is 0. To the power of 0 is 1. Times it by -1, and you're subtracting. All this is equal to +1. So this here should be +1. I'm still thinking maybe I could be wrong. So dt. Oh, wait. It should be a goes to -infinity, not the other way around. That's why I was getting confused. B is equal to 0. Since B is 0, it will become +1. Sorry, -1. Is this correct? Yeah, this makes more sense. Now this time, b is going to infinity. But this is another indeterminate form. No, just going straight up to infinity. A is to 0. So from the positive side, it diverges. It's 1. Integrating a discontinuous integrand. Let f of x be continuous over a to b. Then you do limit b from the negative side. Let f of x be continuous over a to b, and then limit a from the positive side. Okay, what's the next one? A comparison theorem. It is not always easy or even possible to evaluate an improper integral directly. However, by comparing it with another carefully chosen integral, it may be possible to determine its convergence or divergence. To see this, consider two continuous functions, f of x and g of x, satisfying this for x is more than a. Then the integral would be integral of f of x would be less than integral of g of x. A comparison theorem, let f of x and g of x be continuous over a to positive infinity, assuming 0 is less than f of x less than g of x for x is equal to a. If a to infinity f of x is equal to limit, then the same thing for g of x. Oh, I see. If this area is infinity, then for g of x is infinity. And if g of x converges, then f of x converges. One over x doesn't converge, but I think 1 over e to the power of x may converge. And we have to show that this converges, and then we can show 1 over 1 over x e to the power of x converges. Okay, what is this? Laplace transform. The last few chapters, we have looked at several ways to use integration for solving real-world problems. For this next project, we are going to explore a more advanced application of integral transforms. Specifically, we describe the Laplace transform and some of its properties. The Laplace transform is defined in terms of an integral as note that the input to a Laplace transform is a function of time, f of x, and the output is a function of frequency. Although many real-world application examples require the use of complex numbers involving the imaginary number I is equal to root minus 1, in this project we limit ourselves to real numbers. Okay, let's just never mind that. Yeah, I guess I will end the stream here. What's the next topic about? Okay, anyways, I will end the stream here, and guess I'll study this differential stuff next stream.